In this video, we will calculate the ground state of the harmonic oscillator. We already called it 0, but what does it look like? And to answer this, we need to ask a second question, that is, in which basis? Consider this vector here, v. Now, what are the components of this vector? Well, to answer this, we have to draw a coordinate system. So now we can say that this is 1, 2, 3, and here we have 1, 2. So the components of v are obviously 3 and 2. But what if we chose a different basis system, such that here is 1 and here is 2, and on the other axis this is 1 and somewhere up here there's 2? Well, in this basis system, the vector v has components 1.5 and 1. So the object v, the vector itself, is always the same. Same with our ground state 0. But in order to classify it, to say how it looks like, we need to choose a basis system. One possible basis system is the basis in position space. Notice that basis vectors are always given by bra vectors. So for example, if we have the vector psi, we could, for example, choose the position spaces to write x psi, and we then have the function psi of x. Or what we could also have done is choose another basis, maybe the momentum basis, and then we would have psi of p. For this video, let's stick to the position basis. Remember, this doesn't change our ground state. This is just saying which basis we will choose. We will start with the equation that helped us define our ground state in the first place, and that is applying a onto our ground state should give 0. We can now multiply the bra x from the left to this equation. This gives x, then the operator a, vector 0, and this again is 0. Now we need the definition of the annihilation operator. The annihilation operator was given by psi plus I eta. Psi was based on the position operator x divided by the square root of 2 and x0, and eta was based on the momentum operator, so p divided by the square root of 2 and p0. Altogether, we can write this equation like this. We don't write the heads anymore, but be aware that these two are operators. They act in the following way on the state x. Just to be sure, this is an operator, and this is just a variable x. Since x and p are Hermitian operators, we can also let them act on the left side. This gives us the following differential equation. This expression here and here is now a function of x, so we can call it psi 0 of x. If we multiply some constants and subtract one term to the other side, we get the following equation. If you remember the definitions of p0 and x0, we can also write this as m omega over h bar. We now have a rather easy differential equation, where on the one side we have the derivative of some function f, and on the other side minus x and the function again. A good ansatz would be that f is given by some constant g1, and then an exponential function of minus, again some constant g2, and x squared. So let's plug this into our differential equation. We apply the derivative, cancel some factors, and we're left with the result for g2. g2 is m omega over 2 h bar, and this is precisely 1 over 2 x0 squared. With this, we can write down the position space function of our ground state. Psi 0 is given by g1, and then an exponential fraction minus x squared over 2 x0 squared. So how do we get g1? Remember that our eigenfunctions of the harmonic oscillator are normalized, so the inner product should give 1. In position space, this means that the integral over psi star of x times psi of x over all allowed values of x has to be 1. For our size 0, this means that the integral from minus infinity to plus infinity of g1 in absolute squared and the exponential function of minus x squared over x0 squared dx has to be 1. There's no factor of 2 anymore because we multiplied two sides together. This is a very important kind of integral that you should really know by heart. So if you have an integral from minus infinity to plus infinity over the function e to the minus ax squared, this is simply the square root of pi over a, whatever real number a is. And in our case, this a is 1 over x0 squared. This means this integral here is simply the square root of pi times x0 squared. Finally, we have the result for g1. g1 squared is given by 1 over the square root of pi times x0 squared, and using the definition of x0, we can write this as the square root of m omega divided by pi h bar. So now finally we have the final result for our ground state in position space. And the function itself looks like this.